Right. So let us discuss the first part. And here I'm going to introduce this new method. So here I'm using a decimal notation to represent qubit states. So let us discuss what is that. For example, you have number of qubits as a 1. That means we have 1 qubit. Then base states. You know what are the base states for this? That is ket 0 and ket 1. These are binary numbers 0 and 1. But here in the notation, I'm going to use this in a decimal notation, that is a 0 and a 1. That 0 and 1 are a decimal only. Okay. So to represent there exists a 1 qubit, I'm using this as suffix 1. Right. So let me explain what is this. For example, here you have 1 qubit. Okay. So generally we'll take it as a Q naught LSB. So here I'm going to take this decimal notation. This is very crucial. I'm representing this state as a 1. That means I'm taking that 1 stands for on state. For example, if you take this a qubit, it is having two possibilities, either off or on. If it is off, it takes a 0. If it is on, it takes 1. Okay. So, and I will tell you how I got this idea. One, this is nothing but a 2 power 0 actually. Okay, so that 2 power 0 I have taken as a 1. And let us see the second one. Number of qubits. If you have a number of qubits 2, then generally base states in the decimal notation we have 0 0, 0 1 and 1 0 1 1. So in this method, I'm going to represent this as a 0, but 2 qubits are there, and this is a 1 with the 2 qubits, and this is a 2 with the 2 number of qubits, and this is a 3 like this. Now let me explain what are these states. Here we have a quantum circuit with the 2 qubits, then generally we will take like this. Okay, so I hope you know this. And this is, let us suppose q naught, sorry, this is a q naught and this is a q1. Now this is the LSB 2 power 0, I'm taking it as a 1, and here it is I'm taking a 2 power 1, that is a 2. This notation is a very crucial while we are solving the quantum circuit in this new method. Okay, you will understand slowly, no need to get tension. So the idea came from this is nothing but 2 power 0 and this 2 is nothing but a 2 power 1. And let me explain what are these 4 states. For example, you can consider like this. So both states are in off, that is nothing but a 0. Once one is in on, second is in off state, that is 1, and second is on, first one is off, so I can take it as a 2, and both on, so this is nothing but a 3. Okay, right. Like this, if I take another example, that is uh, let me take the number of qubits as a 3. If you have 3 number of qubits, then base states we have 0 0 like this, 0 0 1, let me write, and 0 1 0 and 0 1 1, and the next 1 0 0, 1 0 1, 1 1 0, and next 1. So these are the base states in a binary notation, but in this method I'm going to use this as a 0 with the 3 qubits, and 1 2 3 and 4 5 6 and 7. These are decimal numbers, and this 3 suffix indicates we have 3 qubits, right? So for example, if you have a 3 qubit quantum gate, sorry, 3 qubit quantum circuit, and let us suppose I have 3 qubits like this. I can take it as a q0, q1 and q2. So now I hope you understand. Here the first one I will take it as a 1, 2 power 0, and this is 2 power 1. I will take it as 2, and this is 2 square, 4. Now for example, if you have 4 qubits, I hope you understand the next one is 1, 2, 4, 8. In this method, these numbers are very crucial. Okay, so for example, I have, what is the meaning of this zero state? So here I have 4, 2, 1, 3 states are there. That means 4, 2, 1. You just check how you will get this 0. So 0 state means here 0 plus 0 plus 0. That means all are off. And here 1 we have, this is a 0 plus 0 plus 1. So the only the first one is on and the remaining two are off. And the next, if I take 2, this is nothing but 0 plus 2 plus 0. That means 2 is on, remaining 4 and 1 are off. Next, if I take 3, so this can be written as 0 plus 2 plus 1, and this is 2 is on, this is 0 off. Like this, if I take the 4th and 5 and 6 and 7, so I can write this as a 4 plus a 0 plus a 0, and this is a 4 plus a 0 plus 1, and this is a 6, 4 plus 2 plus 0, and the 7, 4 plus 2 plus 1. That means here all 3 qubits are on, here first two on, the last second third one is off, here these two on, and this is off, and here this fourth one is on, like this. Okay, so if you have 4 number of qubits, its order is a 1, 2, 4, 8, like that. Like this you can take any number of qubits, it's not a problem. Okay, so one more time let me explain briefly. If you have 1 qubit, we will take that as a 1 decimal value, and if you have 2 qubits, you have to take it as a 1, 2, like this, from LSB to MSB. And if you have 3 qubits, you have to take a 1, 2, 4, like that. And a 4 number of qubits, 1, 2, 4, 8. So like this you can take n number of qubits. That means uh, it goes from 1 to 2 power n. So these numbers, these are very crucial in solving this quantum circuits in this new method. Okay, so here now next I'm going to start this single qubit quantum gates and some quantum circuits. Okay, so whenever you have single qubit, you know, basis states we have two, that is a 0 and 1. That means that the dimension of Hilbert space, the dimension of Hilbert space is 2. Then if you have this single qubit quantum gate, it is represented by a unitary matrix. So a unitary matrix of order 2, of order 2. So here I'm taking a more general notation like this. So I'm taking this matrix as a, sometimes you can take alpha and beta, but I'm taking it as a B, C, D, like this. I'll tell you why I have taken like this. Okay. And of course it is a unitary, that means U dagger U equal to I identity. Okay. So here I have three options are there, three cases. The first case I'm taking it as that A, B, C, D element, that elements of that unitary matrix, all are non-zero. That means uh, case 1, A comma B comma C comma D. All these elements are not equal to 0. This part is very crucial. I request you please focus. And here this then U equal to A, B, C, D, like this. And whenever all the elements are non-zero, what it will do, it will create a linear superposition of qubit states. It creates superposition of qubit states. You will understand in the examples, no need to get tension. And the second case, we have, let us suppose this a equal to 0 and d is also equal to 0. That means the diagonal elements are 0, but off diagonal elements are not equal to 0. B is not equal to 0 as well as C is not equal to 0. Then the unitary matrix, we can write it as a 0 C and here B 0. So what this type of matrix will do, it will flip the quantum gates, quantum states, flip the qubit states, flip the qubit states. And I will give some examples for this also. First, let me explain the cases. And the last one, case 3, here we have, and a is not equal to 0 and d is not equal to 0. That means the diagonal elements are not equal to 0, but off diagonal elements b equal to c equal to 0. Then this unitary matrix can be written as a d and here 0 0. And this type of gates, they will add a phase to the qubit states, add phase factor, phase to the qubit states. I request you, first part please watch this properly, then only you will understand the remaining parts. And here I am going to give some examples for this uh, 3 cases. The first case, all elements are not equal to 0. You can take a Hadamard gate, that is a 1 over root 2, this 1 1 1 minus 1. And you can take Rx, and Rx and means rotational operator about x-axis and a rotational operator about y-axis also you can take. So for example, if you have this Rx of theta and Ry of theta, I will write here Rx of theta. This is cos theta by 2 minus I sin theta by 2 and minus I sin theta by 2 and cos theta by 2. If you want that Ry of theta, it is a cos theta by 2 minus a sin theta by 2, and the next element is a sin theta by 2 and the last element is cos theta by 2. And here the case 2 examples where the diagonal elements are 0 and off diagonal elements are non-zero. Here we have Pauli X matrix, that is 0 1 1 0, and Pauli Y matrix, this is a 0 minus I a 0. And the case 3 examples we can take which add a phase to the qubit states. I can take a Z, Pauli Z matrix, which is 1 0 1 0 0 minus 1, and S matrix, that is a 1 0 0 I, and a T, that is a 1 0 0 e power I pi by 4. So this Z gate will add a phase to the qubit state, okay, uh, pi, and here S, this is I is nothing but e power I pi by 2, and here this will add T gate will add e power, I mean pi by 4 phase to the one state. That means whenever the qubit state is on, it will add that phase. If it is in off state, it won't add any phase. That's the point. Okay, and if you see the relation between all these things, you can write a t square. T square means e power I pi by 4 whole square. If you take, you will get e power I pi by 2, which is nothing but I. So that's why t square equal to S. And if I take a t power 4, that means that 4, this e power I pi by 4 whole power 4, you will get e power I pi, which is nothing but minus 1. So that's why I can take a t power 4 as a Z, right? Right. So now let us discuss about this first case. So here I have taken the first case where all the elements I am assuming as a non-zero. Examples we have seen Hadamard gate and Rx of theta and a rotational operator about x-axis and rotational operator about y-axis. And here this creates superposition of qubit states. And in the earlier, we have already discussed all these qubit states. We are using this to represent these qubit states. We are using the decimal notation. Okay. Now, for example, I have a single qubit gate. Let us suppose this is the single qubit gate, which is represented by this unitary operator. Whenever you have only single qubit, you have to take the state notation as a 1. If you have 2 qubits, take it as a 1 2, and if you have 3 qubits, 1 2 4, like that. Okay, so just wait, you will understand what is that. And here the operation is represented by, because this is a single qubit, so operation, this is very crucial. The operation is represented by u of, that means it may be h, it may be rx, it may be ry. So there is no control. I am taking this as a target bit only, because this u operator operates on that state, qubit state. That's why I'm using the word target. So this is a 0 comma t, t for target. Okay. So this target stands for this one, 1. Okay. So either that state will be in off state or in on state. So in this, we can write it as u of 0 comma 1, because here it is a 1. Okay. So that means this operation is creating a superposition state of 0 and 1. How it will create? Now let us. Now for example, I request you please see this matrix one more time carefully. This one, we have two columns, this first one and second one. Okay, so just take like this, and I request you, this is a very crucial. And here we have first column, and this is the second column. Use the first column if the target bit is, if the target bit is in off state. Use this first column if target is in off state, and use this second column as amplitudes for the superposition state if target is in on state. I will explain what is the meaning of this. So now I'm going to take this operation. U is operating on 0. This 0 stands for here off state. So then I have to take the first column, this one, AB, as a amplitudes. That means here I can take it as first one A 0, B plus B 1. Remember, you have to take this order. That means 0 1. First you have to take 0, next you have to take 1. Don't change the order. Okay, and next if it is a 1 and this operation U operation, that means this 1 stands for on state. Then you have to take the second column if the target is on. Then this is a C 0 plus D1. Qubit states are 0 and 1 only, because there is only one single qubit, it available either in off state or on state. So that's why 0 and 1. It creates a linear superposition of 0 and 1 with the different amplitudes. So what I'm saying is, this is 0 stands for off state. If it is off state, target is off, use the first column. If a target is on, use the second column. This is very crucial. For all these single qubit gates, whenever target is on, use the second column. Target is off, it is an off state, then use the first column. Okay, let me explain this by using one example, by taking one example. The first one, here I am taking the Hadamard gate. You are familiar with this Hadamard gate, and you know there is only one single qubit, that's why I'm taking it as a 1. Just now I discussed what is the operation. This is a h of 0 comma 1. That means this Hadamard operator will create the linear superposition of 0 and 1. Now, just here I am using this notation, zeros first one always off and as the second one always on. Whatever the order pair we have, for example, if you have h of 2 comma 3, just assume the first one is off, second one is on. I will explain what is that, no need to get attention. Okay, So the Hadamard operator 1 over root 2, this is 1 1 1 minus 1, sorry. So just now I discussed, just divide that as a first column and second column. Now this I can write at a time, that is 0 and 1. This Hadamard is operate on 0 and 1. Okay, don't take it as a matrix, just take it as a 0 and 1. I'm just writing combinedly. 0 stands for off state, already we have discussed. That's why 1 over root 2 is the uh, outside normalization constant. So for off state, we have to take the first column, that is 1 1. So you have 0 plus 1. Remember, this operator always creates the linear superposition of these two decimal states. These are not binary, please remember, decimal only. And the second one, this 1 stands for on state. That's why I have to use the second column. That's why it creates a superposition of 0 and 1. But now it becomes 0 minus 1. If you want to write this in the ket notation, this is nothing but 1 over root 2 0 plus 1, and this is a 0 minus 1. Now let me take one more example, then you will understand more properly. Second one, I'm using this rotational operator around about x-axis. And we know what is Rx of theta, rotation about x-axis. This is a cos theta by 2 minus I sin theta by 2, and this is also minus I sin theta by 2, and here cos theta by 2. As usual, first column whenever target is off, use the second column whenever target is on. And operation just now I discussed, this is Rx of, this is only single qubit is there, that's why our notation it is a 1. So there is no control, only target, this is a 0 comma 1. So it creates the states 0 and 1 as a superposition of 0 and 1 only. So what does it mean? For example, you have 0, so this is Rx is operating on this, then you have to take the first column because it is off. So this is a cos theta by 2, and here the first one is a 0. You have to take that order only, don't change the order please. 0 and minus I sin theta by 2 1. And if it is a 1, Rx operates on this. Now this 1 stands for target is on, then please take the second column as the amplitudes, minus I sin theta by 2, 0 only, order should not be changed, plus cos theta by 2 1. Let me take one more. Third one, still not understanding. There is a single qubit gate, and this is Ry of theta, rotation about a y-axis. First write what is the matrix. So here we have cos theta by 2 minus a sin theta by 2, and this is a sin theta by 2, and the next one is cos theta by 2. I request you please just take the divide into two columns. First one is for off state, second one is for on state. And this operation Ry of, since we have one qubit, our decimal notation it is a 1. So this is a 0 comma, that is 1. This one we have to take. If there we have 2, you have to take a 2. If that is a 1, you have to take that's 1. When you will get to 2, I will tell you, just wait. Okay, so this is nothing but here I am writing like this. That means 0 and 1 is there. Ry is operating on that. So 0 is off, we have to take the first column, cos theta by 2, 0, plus a sin theta by 2, k2. And the next one, 1 become, you have to use the second column as the amplitudes, minus a sin theta by 2, 0, plus cos theta by 2, 2. Okay, so just I'm writing with this brackets. Okay, no need to get tension. This is get 0, get 1. Remember, all these 0 and 1 are not at all binary, and here strictly I'm following this decimal notation. I feel little bit easy to solve these quantum circuits by using this notation. If you are facing any trouble, please let me know. And now, for example, now you got it out. Okay, you have taken only one single qubit. That's why, for example, we have two qubits and we have combination of a single qubit gates. Then how to solve? That means, for example, let us say we have two qubit states, and here we have u. This is very crucial. And here the first one, nothing is there means we have identity. Nothing is there means identity. Generally, what we will do is we will take the tensor product of from top to bottom, that is I tensor product U. This will give you another unitary matrix. By using that, you can operate. But here we are not using that. Now here really you will appreciate this method, how it is useful to solve this type of circuits. Now listen careful. So two qubit states are there. So I have to take this as a LSB 1 and this is a 2. Now identity, forget about that identity operator. It won't change any qubit state, just leave it. And here we have U operator. I'm representing this as a B, C, D. So this creates linear superposition. And the first column and second column I divided. This is off and this is on. Okay, right. Now see how I'm writing the operations. This is very crucial. Please listen. Now the operation, here it is the U gate. That means U operator, U of 0 comma, here what is the target? 1, 0 comma 1. And what about the other possibilities? Now see here you have another qubit with a 2. You just add plus 2 to the above operation. That is u of u of this 0 plus 2 is a 2 and that 1 become a 3. That's it. That means whenever you have two qubits and a single qubit gate is on that first line, that is LSB, that is 1 here. Okay, then it not only creates a superposition of 0 and 1, it creates a superposition of 2 and 3 also. If you want, you can check by using the tensor product of I tensor U. But this is very easy, very easy. So as usual, first one is off, second one is on. Now see how I'm writing. This is 0, 1, 2, 3. Directly I'm taking, if you don't mind. Okay. Otherwise, I will write separately. So 0 and 1. See here 0 is off, 1 is on. Off means you have to take the first column, that is A 0 plus B 1. Remember, you have to take the superposition of these one 0 and 1 decimal states only. Okay, and the next one we have, this is on, that's why C0 plus D1. That's it. And if I take this 2 3, now see carefully, this 2 is off, that's why A into, remember, U of 2 comma 3 means that gate or that operator creates a superposition of 2 and 3. That's why A2 plus B3. And this is 3 stands for on. This is C. You should not change the order. You have to take the same order, 2, 3 only. Here. Don't see there. Here, please see here. That is a C2 plus D3. I hope you understand. Still not understanding? No problem. So let us take another example. Please listen. And this time I have the unitary operator or a single qubit gate on the second line. So we have two qubits. That's why I'm taking it as a 1 and 2 decimal notation. Now here it is identity, leave it, no need to consider in our method. This is u of 0 comma 2. This time it is on that second line. So that's why 0 comma 2. The remaining is what? 1. So just add that. This is u of 1 comma 3. So total it creates a superposition of 0 and 2 and superposition of 1 and 3 with amplitudes. First column as first column, it use the first column if the target bit is off, it use the second column if the target bit is on. It's very simple. So the first one is always take it as off and second one is always take it as on. So for example, so 0, you can take anything, 0 2 I'm taking, you can take 0 1 2 3 also. Okay, now let me write all together, then you will understand. 0 1 2 3, these are the basis states for 2 qubits. Okay, I hope you know that. And now what this quantum circuit, how this quantum circuit is changing these states, let us see. 0, now please carefully see, here is a 0, here is a 0 which is in off state. Okay, and one more thing you have to see, that creates a superposition of 0 and 2, so that's why off state a0 plus a b2, no confusion, observe carefully. Next one is 1, here you have this 1, 1 is in off state, it creates a superposition of 1 and 3, 1 and 3, so that's why this is nothing but c 1 plus d 3. Oh, I'm sorry, because it is off state you have to use the first column, I'm sorry, that is a 1 plus b 3, superposition of 1 and 3, but you have to use the amplitudes as the first column because it is off. Next second 2, this one, here we have second one which is on state, that's why you have to use c 0 plus d 2. Okay, and last one, third one, so here it is an on state, that's why c, this creates a superposition of 1 and 3, that's why you have to take a 1 plus d3. If you have any confusion, you can do like this also, you please take the numbers of this state or anything, it's okay, no problem. If you have any trouble, 0 2 you can take separately, and after that 1 3 you can take separately. For example, if you take a 0, that is off, a0 plus b2. If you take 2, it is in on, that's why c0 plus d2. If you have any confusion in writing all this together, you can do like this also. And next 1 is, this is off state, that's why a1 plus b3, and this is a c1 plus d3, like this. Okay, now let me explain a small example for this 2 qubits. Two qubit states are there, but a single qubit only we are using in the circuit. Now for example, uh, let me take this example. We have head mod gate here, okay, and here nothing is there, but we have 2 qubits, that means identity is there. So 2 qubit states, here it is a 1 and a 2. I hope you are following. And my this head mod operator, 1 over root 2, 1 1 1 minus 1. Let us write the operations, that is a h of 0. Okay, so your target is 1 here because it is on a first state, and after that you have to add whatever the remaining decimal state is there, that is a 2, you have to add that, that is a h of 2 comma 3. Now see, here I'm taking like this 0 2. So why I'm taking for this head mod like this, you will understand. So my advice, whenever you have head mod gate like this, please take first one 0 2. I'll tell you why it is like this. Okay, now this head mod operator is operating on this, be careful. So 0 is here, okay, so it creates a superposition of 0 and 1, right? And now This is off state, this is off state, and this 1 and 3 are in on state. So that's why 0 plus 1. 1 over root 2 is outside, no need to get tension. Next 2, this is also off state, that's why here I have to use the first column, that is 2 plus 3. Okay, now I'm using the next one, that is a 1 3. Why I'm using like this? It's very simple. You just change the sign of this middle one, that is a 0 minus 1 and a 2 minus 3. Whenever head mod operators are there, you better to take in that order. Anything you can take, it's not a problem. But if you write the first one, second one is very easy, just to change the middle sign. Because here 0 is in off state and 1 is in on state, that's why I have taken the second column. Here 2 is in the off state, I have taken the first column, and here 3 is in the on state, that's why I have taken a second column. Directly we can write. Still not understanding? Let me take one more example. So if I have head mod gate like this is a 1 and a 2 because the 2 qubits are there. Now observe carefully the operations. H of 0 comma 2, and for this I have to add the remaining one, that is a plus 1, that is a h of 1 comma 3. Okay. So I told you first take that column 0 1, like that. I mean first elements in that bracket. Next take the second element. This is for head mod gate, because just only by changing the sign you will get the other one without doing again. So here I am taking a 0 1 head mod gate, operating on this 0 1. 0 is an off, so that's why 0 plus 2. Please see in that bracket what you have, 0 2. So it creates a superposition of 0 2 only, and it is off, that's why take the first column, that's why 0 plus 2. Next 1, 1 is in off state. What are the numbers there? 1 and 3, that's why it is a 1 plus 3. Now what I am saying is, without doing the next one, you can write directly 2 3. Of course outside normalization constant will be there because the two states are there, and this is a head mod gate. No need to do it because the 2 is in on, 3 is in on, that's why 0 minus 2, 1 minus 3. Okay, so still if you are having a trouble, I will take one more example with this rotational matrix. I have two qubits, that's why I'm taking a 1 and a 2, and here I have Rx of theta, and here nothing. Okay, that means identity. So first let me write what is this rotational operator. Cos theta by 2 minus I sin theta by 2 minus I sin theta by 2 cos theta by 2, and take this first column off and this is on. Now come to the operations. This is Rx of, since it is on the first one, this is a 0 comma 1. If the operator is on the second one, 0 comma 2. And next what you have to do, you have to add whatever the remaining, that is a 2, that is Rx of 2 comma 3. Okay, now you can take anything here, it's not a problem. Earlier head mod gate means for head mod gates only I said take the first elements of that bracket. You can take anything, 0 1. So 0 is off and 1 is in on state, so that's why 0 off, you have to take a cos theta by 2 0 minus I sin theta by 2 1. You have to take the first column, and 1 is in on state, that's why minus I sin theta by 2. You should not change the order. 0 plus a cos theta by 2 1, that's it. And the next one 2 3, this is not only Rx, sorry, this entire this entire circuit. and here 2 is in off state and 3 is in on state. That's why I'm taking cos theta by 2, but it creates a superposition of 2 and 3, so that's why minus I sine theta by 2 3 here, and that 3 minus I sine theta by 2 2 plus cos theta by 2 3. That's it. Okay, so now you got a doubt. For example, I have 3 qubits, then somewhere in the middle I have a single qubit gate. Then how to do this? I will explain one example. After that you can do it. Now for example, I have 3 qubits states. Let us say like this. And what is our decimal notation here? 1, 2, 4. Fine. Now for example, you have this single qubit gate on the second one, and remaining are empty, means we have identity operators. Then you have to, if you want to create the entire unitary operator of the circuit, you have to take the tensor product of I, tensor U, tensor I. So I hope you know this. This method already is there. Okay, but without finding the tensor product, we are writing here. So then how to get these operations? Now listen carefully. Always we have to take the first one as that operation, that operator U, on which state it is a second state. That's why I am taking it as U of 0 comma 2. And then you have to add. Which one you have to add? Then you got it out. Remember, anything you can add, either 4 or 1. But my advice, so please add least one, least to highest. That means first I am adding plus 1. This is very crucial. I request you please listen. Now you got the two operations. It will create the superposition of 0, 2 and 1, 3. Next, one more is left. What's that? 4. That fourth one you have to add for these both. Okay. That means you have to add 4 to this both operations. Then you will get another two operations, that is u of 4 comma 6. This is u of 5 comma 7. Okay, so this is the technique. Or for example, if you add first 4 here, then you will get 4 comma 6. Then you have to add 1 to both the operations. So total it creates 4 operations: 0 2, 1 3, 4 6 and 5 7. That means it will change 0 2, I mean it creates a superposition of 0 2, 1 3 and 4 6 and 5 7. If any number is not there, means there is no change. That's the point. Okay, so I hope you understand this 3 qubits. Let me take one small example, then you will understand. So one more time I'm saying you have 3 qubits. So 1, 2, 4, and I'm taking this head gate here, and the remaining are identity. Okay, so if you want, you can take identity. Then by using our notation, how to write these operations? This is a h of 0 comma 2. Now you are here, I hope you understand. Anything you can add, but I am adding a lowest number to highest number, like that. So first one I am adding 1, that is a h of 1 comma 3, and this is a plus 1. So for this both we have to add a 4. That's why it become h of 4 comma 6, and this is a h of 5 comma 7. Then how to write? I told you already, please take the, whenever head mod operation is there, please take the first elements in the bracket, that is 0 1, and here 4 and 5 are off, and the second one is in on state. I'm taking 0 1 or 4 5. So at a time I can take, no issue, because the second one is very easy to write. I head mod operation. So the 0 is in off state, it creates a superposition of 0 2, and a head mod operator, 1 over root 2, 1 1 1 minus 1. So please take the first column if it is off, and take the second column if it is in on state. 0 off state, that's why 0 plus 2. 1 off state, 1 plus 3. I hope you are observing. And 4 off state here. Okay. So then it creates a superposition of 4 and 6. So that is 4 plus 6. And next we have 5. It creates a superposition of 5 and 7. And this is a 5 plus 7, because the first column we have to use. And once you have written this, you can take the normalization constant 1 by root 2, because the two states are there. And now it's very easy to write the other states, that is a 2, 3, 6, 7. I'm taking the second elements in the bracket, which are in on state. All these are off and all these are on. Especially whenever you are dealing with this head mod gates, better to take like this, because without doing anything, directly we can write the middle one. Whatever the middle sign we have, just change, just take opposite. That is 0 minus 2, 1 minus 3, 4 minus 6, 5 minus 7. But whenever you are having some other combination of quantum gates, maybe sometimes you will get a minus here, then you have to take the opposite plus. That's it. You will get the answer directly. So that's it. If you want, you can check with the tensor product also. It's not a big deal. Okay, right. I hope you are understanding this method. If you are facing any trouble, so please let me know. Okay, now let us go to the type 2. So here I'm taking this type 2, where we have this unitary matrix, this A, B, C, D, and I'm taking this A as a 0 and D as a 0, and C and B are not equal to 0. That means this is a 0, B, C, 0. So we have already discussed, and what it will do, it will flip a qubit states. So this is just an alternate way or alternate method to solve these quantum circuits. Okay, so fine. Now examples, if you have, let me take it directly. So because I have already explained that operation, that is 0 comma t, t for a target, whatever you have. So I'm taking this single qubit x. So here we have single qubit, that's why it is 1. Now this operation is represented by x of 0 comma 1. Now earlier I told you u of 0 comma 1, it creates a superposition state of 0 and 1. Now this is a Pauli X gate, and type 2, what it will do, it will flip the qubit states. That means it flip 0 and 1, 0 to 1, 1 to 0. So that means you need not to find any matrix, directly you can write 0 to 1 and 1 to 0. Okay, right. And if I take a second one, let us take a Pauli Y gate, a single qubit gate, and since it is a single qubit, it is a 1. And let me write this X matrix also, then you will understand. This is a 0 1 1 0, and here this Y operator, 0 minus I 0. Observe carefully, this is also superposition only, because once the first one element is a 0, one amplitude is 0, that's why I'm using that. It is flipping the quantum state or something like that. This is also superposition only. This is off and this is on. Now the operation is represented by y of 0 comma target. Here target is 1. Now 0 stands for off, 1 stands for on. So 0 operates on this, y operates on this 0 state. We have to take 0 I. That means flip with the phase. Observe carefully. It will flip and add this phase. And if the target is on, it will flip the bit, qubit, and add this phase. So I hope you understand what I'm saying. First column contains I, that's why I1. Flip with some phase I. And 1, so it flip 0, but with the phase factor minus I. Okay, that's it. So you can represent like this also. Whenever you have 0 state and 1 state, if this is X gate is there, 0 to 1, 1 to 0. And if it is a Pauli Y gate is there, you have 0 and a 1. Remember, all these are decimal states only, decimal notations. The qubit states, but I am using the decimal notation because it is a single qubit. That's why as a both are similar only, 0 and 1 only. So 0 to 1 flip with a phase factor I, 1 to 0 flip with a phase factor minus I. Next, let us take type 3. I hope this is type 2 and type 3. Here I am taking this diagonal elements are non-zero, that is A, D, and off diagonal elements are 0. So this will just add up because you will get the same state again. That's why I'm using the word, it will add phase to the qubit states. This is also superposition. Okay, add a phase to qubit states. Okay, so as usual, you have to divide this into two columns. First column if the target is off, second column you have to use if the target is on. Now I'm taking a directly example. This is JET gate. So here single qubit, that's why it is represented by 1. Okay, and the operation is as usual same, that is a 0 comma 1. Remember, so 0, first one is off, second one is on. Always first one is off, second one is on, like that please take. Okay, now so just it will add phase to the qubit state, it won't flip any bit, any qubit. That means the 0 become 0 with the phase of that here. Here we have A, but in this case Z is nothing but 1 0 0 minus 1. This is off and on, that's why it is a plus only. And next if I take 1, it is in on state, I have to take the second column, that's why minus 1. Let me write here also. So here 0 to 0 become A into 0 and 1 become D into 1, like this. If you have a single qubit and this is a 1, operation is U of 0 comma 1. Let me take one more example, and here I have the the phase gate S gate. So operation is here it is 1, S of 0 comma 1, and S matrix. Let me write the S matrix here. This is 1 0 0 I. This is off, this is on. Now here I have 0 1, and this S gate operates on 0 and 1. So since 0 is off, 1 is on, so no change, that is a 0 only. If it is a 1, it add a phase of I, that is a I1. So I can write this as a 0 and this is I1. And let me take one more example, third one. This is a T gate I am taking, single qubit 1. So the operation is a T of 0 comma 1 and T operator unitary matrix 1 0 0 e raised to I pi by 4. So this is off, on, and first column off, second column on. So that's why the 0 1 gives 0 no change, and 1 will be having a extra phase factor of e raised to I pi by 4 1. So if you have a problem, you can add this Dirac notation like this. Okay, so whether it is type 1 or type 2 or type 3, We are taking that matrix and using the first column as the amplitudes if target bit is off. We are using the second column as the amplitudes if the target bit is on. Now you got one more doubt. So you have explained separately if I have the combination of, let us say, this H, Z, T, or something like that. If all these gates are there, then how to solve? I will explain that also. Okay. So now here I am taking some examples involving single qubit quantum gates. Now first one, here I have this two qubits I am taking. Okay. So here I have H, and let us say this is a Z. So please use our notation. Two qubits are there. So that's why here I am taking 1 and 2. Observe carefully. See here, you can take, generally will take from, whenever you are taking the tensor product, you will take top to bottom. But this operation, it's not a problem. But my advice, please take from top to bottom only, or you can take anything, because the reason is a Z you can slide like this. That means a Z is operating first. If you just slide H this side, that H is operating first. Here I'm going with the operations, not a tensor product. Okay, so that's it. I can take anything. So I'm taking H first. H of, I hope you understand already. It is here 1. That's why 0 comma 1. But remember, one more qubit left. That is a 2. You have to add. That is a H of 2 comma 3. Just strike a line. We have one more gate, that is Z. Z of 0, because there is no control. The target is 2. But this time you have to add 1, because 1 is remaining. That is Z of 1 comma 3. Then how to operate this combined? This is very crucial. Now I told you, whenever head mod is involving, so better to take that first elements of that bracket, that is a 0 and a 2. Okay, I'm taking that 0, 2. Observe carefully, it's easy only. Now first I'm operating a H, because anything you can take, either H or Z, because it is operation, not a tensor product. H you can take, it's not a problem. So 0 is off, and first one is off, second one is on always. Already we have seen that head mod gate, no need to write that head mod operator or matrix. 0 off state, that's why it creates a superposition of, be careful, it creates a superposition of this one, 0 and 1. Okay, right. So that's why this is a 0 plus 1. And the next 2, 2 is also in off state, but it creates a superposition of 2 and 3. Off state means first column 2 plus 3. Next, Z is operating on that. Now come to this Z operations. Already we have seen Z operation, it won't change, it won't flip any state. Okay, it will just add a phase factor. For which one? If it is in on state. Which states are in on state? It's very easy to observe. 2 and 3 are in on state. 0 and 1 are in off state. That's it. So here 0 off, that's why 0 only. 1 off, that's why 1 only. Next 2, it is in on state, that's why minus 2. And the next 3, it is in on state, that's why minus 3. Over. Next, we have to take another one, that is 1 3. 1 3 here. That means the next elements of that bracket, that is 1 3. This is what I said. Whenever you are having head mod, if you take like that, this is the advantage. You need not to do it again. For example, this 1 is in on state, that's why here you will get a 0 plus, sorry, on state, that's why I have to take the second column, 0 minus 1. See, if you observe carefully, here plus is there, I am taking minus here. And a third, sorry, 3, it is in on state, that's why 2 minus 3. Without doing all these things, we can directly simply change the sign in the middle. Please remember this one. So here 0 minus 1, 0 plus 1, and here, oh, I'm sorry, here. So this is the first answer, and if you want to get the second answer directly, whatever the sign in the middle, just change that. 0 minus 1. Here sign in the middle is minus, that's why minus 2 plus 3. That's it. If you want, you can check. So Z is operating on 2. So here 2 is on, that's why minus 2. And 3, that is on state. That's why Z operate on minus 3. It will become plus 3. That's it. So this is what I am saying. Uh, if you have header mod operator, take this 0 to first, and after that 1 3 next. Okay, now that's it, because we have two qubits. And take one more example, still not understanding. If you have any confusion, take one more example. Let me take a H here, header mod, and I'm taking a T. Okay, right. So this is a 1 and here it is a 2. First you have to write that decimal states, and now operations. Observe carefully. I can write H first, next T, or T first, H next. It's not a problem. Operations, no issue here, because uh, there is no control here. It's okay. Now I'm taking H. So 0 comma it is on 2, and you have to add the next one. Remaining is 1. That's why H of 1 comma 3. You have to add that 1 to both the elements of that bracket. And the next T, it is on first state, that's why 0 comma 1, and I have to add 2 now, that is a 2 comma 3. And always off and on, first one is off, second one is on. Okay, right. Head mod is, I hope you understand. If it is off, plus plus, if it is on, plus minus, that means second one is minus. And if you forget this T operator, 100 e power I pi by 4 I am taking. And head mod also I will write, if you want, 1 over root 2, 1 1 1 minus 1, off on, and this is off on. Now here also I am taking, I told you 0 and 1 I am taking, because here see this one. If it is a head mod, I will take like this. Otherwise anything you can take, it's not a problem. Okay, uh, sorry, head mod is operating on 0 and 1. 0 is off, it creates a superposition of 0 and 2, 0 plus 2, because off. And next 1, it is also off, but it creates a superposition of 1 and 3, so that's why it is a 1 plus 3. Next T is operating. Now observe carefully, 0 off, no change, 2 is off, no change, but 1 is in on state, because second one is on, second element in that bracket is on, first element in that bracket is off. 1 on, that's why it will add a phase factor of e power I pi by 4. I'm using that Dirac notation. 3 is also on, e raised to I pi by 4, 3. Here also you can use if you want, it's not a trouble. Now the next one, no need to do it directly, you can write the next remaining second column. If I take here, this is a second column, then I will write it as 2 3. This is the advantage. Directly here I am writing, trying to write the answer. You please do it and check. So just I am changing the sign in the middle. This is the middle sign, that is 0 minus 2, and this is e raised to I pi by 4 1 minus e raised to I pi by 4 3, like this. Okay, right. So like this we can do. Now you got a doubt. So whether this is right or wrong, how to check? For this I will use this quantum simulator, circuit simulator. Wait, just wait. Okay, now please take that first one, that is a Z and a H gates. So I'm taking this this one. Okay, so here first I am taking Z, and this is a H. So if you have 0 0, that is a 0, and here one small issue is there, and whatever the state we are having, if you click that, so that is showing that 1 0. Remember, you have to take it in a reverse way. Okay, so in this they are taking top to bottom, but I am writing bottom to top, so that is a small correction you have to take from this. But don't worry, it's correct only. I have verified with this matrix multiplication also, and if you want, you can also check with the tensor product. And here 0 0, that means if you see the first one 0, final answer is this one, 0 and 1. Now if you see that circuit, they are showing here 2. That's what I am saying. They have given that ket 1 0. Please observe that 1 0. Okay, sorry, yeah, 1 0. You please take it in a reverse one, a 0 1, then it is a decimal 1. Okay, so this is simulator and my method, that is having a small change, that is I have taken from bottom to top and they have taken top to bottom. Okay, so and the next one is a 0 only, that's not a problem, all are zeros, that's why there is no change. And see the next one, I'm taking a, here changing the 1, that means here I have taken one decimal, but one decimal, that is a 0, sorry, 0, and this is 1. So let me go through this. 1, here you have 1, so 1 become 0 minus 1. Of course 1 by root 2 will be there. So here let me write this normalization factor, I forgot, 1 by root 2. Okay, and here also let me write finally 1 by root 2 is the normalization factor. Okay, although if I forget that normalization factor, I hope finally 2 states are there, take 1 by root 2, 3 states are there, take 1 by root 3, 4 states are there, take 1 by root 4. Okay, right. uh yeah, here we are checking this one, we got 0 minus 1. Now see that circuit, here this one 0, phase is a 0 only, no problem. And this a second one, phase is 180, that means minus 1. Okay, uh, and this is a small confusion to you, but don't worry, it's exactly right whatever I'm saying. So you just change the order, it's not 1 0, it is a 0 1 and the decimal 1, that's it. And can check 3, that is both I have taken 1 1 input. Okay, then here we have a decimal 1, but remember that is a decimal, not a decimal 1, it's a decimal 2, because we have to take from bottom to top, that is a 1 0, it's a 2. And phase is a minus 1, because 180 degrees phase is there, we will get minus 1. And this one 1 1. So let us check, here we have 3, this is minus 2 plus 3, exactly. So here this is 2 only, one more time I'm saying, and this is a 3. 3 is having a phase plus 1 here, I mean 0 phase, that is a plus 1, and this phase is 180, we have minus. Like this you can check the second one also, if you want I will check, that is a HT. Okay, so here the first one I'm taking H, and next I will take this HT. So here already we have taken input as a 1 1, that means a 3. So let us check, and this is a combination of decimal 2 they have given, but remember it is a decimal 1 with a plus 45 phase change, and the next decimal 3 with the phase change minus 135. Okay, let us see. And here, sorry, here I am checking this third one. Okay, so see, this is the phase difference, pi by 4 plus 45 and 1 only, it's not a decimal 2, it's a 1. As per my notation, it's a decimal 1 only. If you want, you can check that tensor product and check, you'll get this one. And third one, we are having a minus pi by 4. Minus stands for what? That e power I pi or minus I pi and pi by 4. If you add, you will get 135. 3 pi by 4 you will get minus 3 pi by 4 you will get. So that's why you are having this minus 135 here. Minus 135. I hope you are seeing this. Like this you can check. And the last one I would like to discuss about this Hadamard gate. If you want one more example, I will take. If still having confusion, I will take one more example. So here I have two qubits. That's why I'm taking 1 and 2. So here I'm taking this Hadamard, and here I'm taking this Rx of theta, rotation about x-axis, and here this Hadamard gate I have taken. Okay, so I hope you remember these matrices. Now let me write the operations first. So this is a h of 0, it is on 1, that's why 0 comma 1, and you have to add the second one, that is a h of 2 comma 3, and here Rx, it is on 2, that's why 0 comma 2, and next one you have to add 1. Okay, so since it is a Hadamard, first I am taking a 0 2. Okay, right. So 0 is off, that's why 0 plus 1. See, directly I am writing because it creates a superposition of 0 and 1. And a 2, that is also off, it creates a 2 plus 3. Normalization constant finally I will write. If you otherwise, if you want, you can write here. And the next Rx operation. Okay, so Rx operation, this is off and on. Maybe if you forget, I will write that Rx theta cos theta by 2 minus I sin theta by 2 minus I sin theta by 2 and cos theta by 2. Now here we have this is off and on. Okay, so let us see. No need to get tension. So here you have 0. 0 is off. Come to this Rx operations. Now you are operating Rx. 0 is off. That's why cos theta by 2. Remember, it creates a superposition of 0 and 2. Cos theta by 2 0 minus, I have to take the first column, minus sin theta by 2 2. Okay, and here I have no space, that's why I'm using plus here, this middle plus. Next 1. 1 is also in off state. Here see this first one, 1 here off state. That's why the same thing, cos theta by 2, but it creates a superposition of 1 and 3. So cos theta by 2 1 minus I sin theta by 2 3. This is the first one actually. Okay, and the next one, if you take this 2, 2 is in on state, that's why uh, minus I sin theta by 2. 2 here we have 0 2, that's why superposition of 0 plus cos theta by 2. You have to use the second column plus. Okay, and the next one 3, that is you have to use the second column, but 3, it creates a superposition of 1 and 3 minus uh, sin minus I sin theta by 2 1 plus cos theta by 2 3. Okay, now you need not to worry about the another one. So just now I told you the next column here, the sorry, next elements here 1 and 3 I'm taking. So this 1 3, I need not to do all these things. Where is the middle sign? Please observe. The middle sign is this one. Just change that. So here cos theta by 2 0 minus I sin theta by 2, sorry, 2 minus cos theta by 2 1, just I'm taking a bracket, minus I sine theta by 2 3. Okay, and the next one, this is minus, here this is the middle sign I am changing. Please observe carefully because only this middle sign will change. So minus I sine theta by 2 1 plus yeah, sorry, 0 plus cos theta by 2 2, the middle sign plus, here it is minus I sine theta by 2 1 plus cos theta by 2 3. Like this we can write directly. Now let us check whether this is right or wrong. Okay, but in this simulator it is not possible to check, but better to take some theta value and you can check. So here the first one is Rx. Okay, so I'm taking this Rx, and the next one is Hadamard 0, and this is a 0. If you observe carefully, all four states are there. Please check. I hope you are observing. And which one are having a phase change? This one, left top one is having phase 0, that is a 0. And here, I told you already, don't take it as a 1 0, please take it as a 0 1. That is also having a no phase change. So 0 and 1 no phase change, but uh, 2 and 3 are having a phase difference minus I, because there is a, sorry, minus I pi by 2, minus I pi by 2, e raised to minus I pi by 2 something. Let us check what we got. Mm, yeah, this one. See here carefully. So 0 and 1 we are having a plus, if you observe carefully, but 2 and 3 we are having a minus. Or if you just give some theta value here, now let me change this. I'm taking it as a pi by 4. Shall I take pi by 4 or pi by I'll take pi only, pi by 2. See, only two states are there. Maybe somewhere you got a cos value or sine value, maybe 0. So just substitute theta is equal to pi by 2 here and check. Now I'm taking a theta as a pi by 2. 1 minute. I'm sorry, here I have taken pi. Okay, so if I take a theta as a pi, okay, then we got only two states. One is 3 with the phase difference with the phase minus 90, and another one here it is 0 1 means 1 0 2 with the phase difference minus 90. Now let us check. Now theta is equal to, we have taken pi, then cos pi by 2 0. So that's why we have, for 0 state we have minus I 2, that means 0 2, let me write properly. Then final answer here I am writing cos 90 0, this is a minus I 2 and this is a minus I 3. And similarly 1 3 if I take, and this also cos 90 0, and here it is, oh I'm sorry, I have to write like this, minus I 2 minus I 3. And second one cos 90 0, cos 90 0, that's why it is a minus I 0 minus I 1 and 1 3. Okay, so this is minus I 2 plus I 3 and minus I 0 and plus I1. No need to worry, just change the middle signs. you will get the second one as whenever you have this head mode operation in the beginning. That's it. You can check like this also. If you want, you can take theta as a pi by 2 also. Let me write so pi by 2. Okay, now then you will be having a four states. Why? Because this cos pi by 4, sin pi by 4, nothing will be 0. That's why you'll be having a combination of superposition of all those four states, 0, 1, 2, 3. That's it. Okay, so I hope you understand this method. So I will give a few examples, so try yourself. Okay, if you are facing any trouble, please let me know. And here head mod I am taking here, this time r y of theta I am taking here, and the second one try yourself. And here rx of theta, and here ry of theta. And third example I will give, let us take a z here, and rx of theta. And fourth one, let us take mm, yeah, so take both head mods, try to do it. Okay, so these are four examples. I request you please try and start like this: 1 2 1 2 1 2 1 2, like this, and write the operations first, and then uh, take the initial state and proceed. Okay, if you are facing any trouble, please inform. Okay, so thank you. I hope you understand this new technique, and in the next lecture, you like more, because two qubit quantum gates, whenever we consider, uh, if there are many quantum gates, you will get you will face difficulty to solve the quantum circuit. But with this method, it is very easy, and we will discuss about the two qubit quantum gates in the next lecture. Okay, thank you.